Hello, everyone. My name is Sergey Slotin, and like many of you C++ enjoyers, I like writing efficient code. And I also like teaching and writing. And recently, I combined these passions and wrote a book on the topic of performance engineering. It's called Algorithms for Modern Hardware. It is hosted on GitHub and is freely available online, so take a look if you're interested. And while working on it, I try to optimize various classic algorithms and data structures, the ones that you read about in textbooks, both out of curiosity and for pedagogical reasons, to use them later as case studies in the book, and succeeded in speeding up quite a few of them. But in this talk, I'm not going to pick just one of these algorithms. Instead, I will discuss a broad topic that is crucial for algorithm design, and especially for data structure design and for programming in general, memory, and more specifically, the CPU cache system. So why should you care about memory? Consider this fundamental question. How long does it take to add two numbers, two integers together? Well, that depends on what you mean. More specifically, on where these numbers are stored. If the values are stored in CPU registers, then we only need one instruction. Not all arithmetic instructions take equal time, but being the simplest and also one of the most frequently used instructions, the addition only takes a single CPU cycle to execute. So if the data is already loaded into registers, it takes just one cycle. But in general, we need to fetch the operands of this instruction from the memory, perform the addition itself, and write the results back where they are needed. And this can get much more complicated. When you fetch anything from memory, there is always some latency before the data arrive. And this latency depends on many factors, but mainly on where the data is stored. You see, modern computer memory is hierarchical. It consists of multiple cache layers of varying speed and size, where the higher levels typically store most frequently accessed data from the lower layers to reduce latency. Each next level is usually an order of magnitude faster, but also smaller or more expensive. This is a mental model of how the cache hierarchy works. It neglects many of the important details, but it is a good starting point. So to answer this question, how long does it take to add two numbers together, depends on where the operands are stored. If the data is already in registers, it takes one CPU cycle to execute the instruction. If the data is stored in the main memory, it typically takes around 100 nanoseconds or about 200 CPU cycles to fetch it. And then probably around another 200 CPU cycles to write it back. But it was accessed recently. It is probably cached and will take less than that to fetch, depending on how long ago it was accessed. It could be around 40 cycles for the slowest, largest layer of cache, and around 4 to 5 cycles for the fastest, closest to the processor. But it could also be stored on some type of external memory, such as a solid-state drive, a hard drive, or some network-based storage that is memory mapped to so that it appears to the programmer like the data is in the main memory, but when you access it, the operating system interrupts the program execution and talks to the device that stores it to return the data. In this case, the delays are so much larger than they are psychologically perceivable, measured in milliseconds of real time and millions of CPU cycles. So because of these huge timing differences, before optimizing anything else in your program, you really need to optimize its memory efficiency. And to perform more fine-grained optimization, a simple awareness of the cache hierarchy is not enough. You also need to take into account the many specific details of how the CPU cache system works. And in this talk, over the next 50 or something minutes, I will discuss these finer details and hopefully teach you how to make use of them in real applications. And instead of giving you just dry facts from boring spec sheets and talking about theoretically achievable limits, I will showcase the many features of the memory system through experiments. By running small benchmark programs with very specific access patterns that often resemble the ones that occur in practical code, and give a few examples of how this knowledge may be useful in the real world. So, there are many different cache layers between the CPU registers and the RAM, and the layers closer to the processor are smaller in size, but also faster, right? And the word faster can apply to two closely related but separate timings. First, it can mean the delay between the moment when a read or a write is initiated and when the data actually arrives, the latency, or it can mean the amount of data that can be transferred per unit of time, the bandwidth. It's important to understand that one is not just the reciprocal of the other, far from it. In the A plus B example, we cared about latency, but for many algorithms, uh, the most important characteristic of the cache system for many algorithms is the memory bandwidth. And at the same time, it is also the easiest to measure. So we're going to start with measuring bandwidth. To measure it, we can write a little program where we create an array and iterate over it, incrementing its values. We time the whole thing and run this loop many times to mitigate cold start effects and to make measurements more precise. To reproduce this and basically all other experiments in the talk, you can compile it yourself with your favorite compiler, but make sure to set the highest level of optimization, importantly enabling vectorization, and unroll the loops so that the cost of loop maintenance itself does not significantly affect the measurements. All benchmarks will be run on AMD Zen 2, a particular CPU microarchitecture, but the conclusions that we will draw are generally applicable. So if you run it with many different array sizes on the x-axis and expressing the total running time as operations per second by normalizing it, we get a graph like this. And you can clearly see the cache sizes on this graph represented with dotted lines. When the whole array fits into the lower layer of cache, the program is bottlenecked by the CPU rather than the L1 cache bandwidth. As the array becomes larger, the overhead associated with the first few iterations and the loop itself becomes smaller, and the performance gets closer to its theoretical maximum. But then the performance drops, first to about 12 to 13 billions of operations per second when the array size exceeds the size of the L1 cache, and then gradually to about 2 billion operations per second when it can no longer fit into the L3 cache and has to be read from the random access memory, which is an order of magnitude slower. And this situation is typical for many lightweight loops. So the broad lesson here is that when the data set is large, what you really want to optimize is not the number of arithmetic operations, but rather the amount of data read from the main memory. The common way to do this is to fuse operations together as much as you can, especially in the context of loops. It is beneficial to join two loops together, not only because it reduces the overhead of maintaining the loop itself and helps with optimization. For example, if the operations in two initial loops are using different parts of the CPU, they can be executed concurrently, so for free, essentially. But also, and very crucially for big inputs that don't fit into the cache, it helps with bandwidth. You can read the array just once and not multiple times. This issue is particularly painful when you are working with high-level abstractions, because the separation of concerns principle dictates that we should implement separate operations that do not know about the existence of each other, but this naturally conflicts with optimizations such as the loop fusion. But let's get back to experiments. In this run, Turbo Boost was turned off, and the CPU was running at fixed 2 gigahertz. With Turbo Boost on, it can run at up to 4.1 gigahertz, more than 2 times faster. All CPU cache layers are placed on the same microchip as the processor. So the bandwidth, latency, and all other characteristics scale with the clock frequency. The RAM, on the other side, is separate from the CPU and lives on its own internal clock. And its timing remain constant, which we can observe on the RAM portion of this graph. This detail often comes into play when comparing different algorithm implementations. When the working dataset does not fit into the cache, the relative performance of the two implementations may be different depending on the CPU clock rate, because the RAM remains unaffected by it, and everything else scales with it linearly. So you might have two implementations, and one of them is faster than at a certain clock rate, but slower at another clock rate. So for this reason, it is advised to keep the clock rate fixed And so we will run most of our benchmarks in this talk at plain 2 gigahertz. There is also actually a problem with this experiment. What we are really measuring is not bandwidth. In our benchmark, we are incrementing array cells. That is, we are reading values and writing them back. While in many applications, we may only need to do reading or to do only writing. So let's try to measure unidirectional bandwidth. To make the CPU generate only read requests, we can calculate, say, the sum of the array. And zeroing out an array or filling it with any other constant value only requires memory writes. It doesn't need any reads. Same as with incrementing loop, these two loops can be easily vectorized by the compiler, and the second one is actually replaced with mmset. So the CPU is not the bottleneck here. If we run all three and plot together, we get a graph like this. First, all three loops perform the same, but then the performance of the incrementing loop drops, but not dramatically when we cross the L2 boundary, because it needs to perform both reads and writes, and only read and only write loops perform roughly the same, which is expected. But then something interesting happens. Unlike the caches, the CPU and RAM are connected with a single dual-purpose bus that can at any point of time be used as either read or write requests, but not simultaneously. So this is like a single lane road, and the direction of this load or this road, this memory bus, is periodically switched by the memory controller, depending on the number of pending read and write operations. So the program that does both reads and writes naturally consumes twice as much RAM bandwidth as the one that only does reads. So, but the really interesting thing, really interesting anomaly is that the write-only loop in green here has the same performance as the incrementing loop on this RAM portion of the graph. In fact, it starts in the L3 cache. Why might that be? This is because the CPU moves the data to the highest level of cache on each axis, whether it was a read or a write. This is typically a good optimization, as in many use cases, we will likely be needing this data that we just have read or just have written again soon. But reading data, when reading data, this isn't a problem, as the data travels through the cache hierarchy anyway. And but when writing, this causes another implicit read on the same data to be dispatched right after a write. And thus, we will be requiring twice as much bandwidth, despite that we will only be doing reads. So these read backs after writes to maintain cache coherency doubles the RAM CPU traffic. And this is why the only write loop performs the same as read and write. We can prevent the CPU from prefetching the data that we just have written by using so-called non-temporal memory accesses. To do this, we need to re-implement the zeroing loop directly without relying on compiler auto-vectorization. And ignoring some special cases, the optimal way to implement memset is to move 32-byte chunks of zeros into the destination with vector operations, which we can implement manually with some intrinsics. So this intrinsic moves 8 zeros, or a full vector registers of 32 bytes into a certain specified locations, and we iterate in 8 elements. So with one instruction, we fill 8 elements with zeros. This particular CPU can execute one write operation per cycle, and with each write operation, we will be writing a vector of 8 zeros into the memory. At 2 gigahertz, we will be executing 2 billion cycles per second, and multiplying these numbers together, we'll get a theoretical upper limit of 16 billion iterations per second, or theoretical memory bandwidth of 64 gigabytes per second, because each number written is a 4-byte integer, which we actually almost reach here. By the way, the compiler also uses simmed operations for the read-only and read and write loops, but it is a bit more complicated than just writing zeros. And this talk is not about simmed, so I won't explain how they work exactly. But now that we have implemented memset ourselves, we can replace the usual vector store intrinsic with a non-temporal one. The non-temporal memory reads and or writes are essentially a way to tell the CPU that we won't be needing the data that we just have accessed in the future. So in our case, there is no need to read the data back after a write. And so the memory system won't execute the implicit read back after this non-temporal write operation. So if we add it to the benchmark, we get a picture like this. At the left side of the graph, if the array is small enough to fit into the cache, and we actually access it at some short time after, this has a negative effect because we have to write it into the RAM each time instead of writing it to a locally cached version. And on the right side of this graph, when the array is too large to fit into the cache anyway, this prevents readbacks and lets us use the memory bus more efficiently. In fact, the performance increase in the case of the RAM is even more than twofold and is faster than the read-only loop, despite both request types using the same bandwidth. This happens because the memory controller this way doesn't have to switch between reading and writing, and also because writes are simpler. The memory controller can just fire and forget a non-temporal write requests without tracking them, which allows more concurrent write operations compared to the read-only loop. Also, if you didn't notice, we just sped up memset by a factor of 3, although only for a very specific use case when we don't need the data that we wrote right away. And most of the time, we actually do need this data, which is the reason why memset doesn't do it. And we can do the same with memcopy and other similar operations. There is also a non-temporal read operation. And if we don't need the source or the destination of the memcopy data right away, you can get similar performance improvements by replacing memcopy with a non-temporal memcopy. So the lessons are RAM and CPU caches are different. L1 and L2 caches are like 2-lane roads, and but shared L3 caches and the RAM are like 1-lane roads. This is important for performance estimation. In many algorithms, in many memory-bound algorithms, you can just calculate how much data transfer you need and divide that by the memory bandwidth, and you get the total running time. But here you need to take into account if it's read or write bandwidth. And your estimates for the lower caches and the RAM will be different. The second tip is use non-temporal reads and writes for the data that you know you won't be needing. So first, this can reduce memory bandwidth, like we've seen, and also it doesn't kick out the data that already stored in the cache, which can also be beneficial. Next, let's try and measure latency. The time it takes to fetch just 1 byte from the moment of the request to the moment you can actually use it. Despite that bandwidth is a more complicated concept, bandwidth was much easier to observe and measure than latency. You can just simply execute a long series of independent read or write operations, and the CPU scheduler, having access to these instructions and device, reorders and overlaps them, hiding their latency and maximizing the total throughput. But measuring latency is harder. To measure latency, we need to design an experiment where the CPU can't cheat by knowing the memory locations we will request in advance. The only way to ensure this is to generate a random permutation of size n that corresponds to a cycle and then repeatedly follow a permutation. So we are generating first a random permutation, and then we are creating a cycle queue out of this random permutation that follows the indices that are in this random of this random permutation. So this is essentially a random cycle, and then we are starting at some element of this cycle, and we are jumping to the another element that the current array cell points. Um, we run it, and compared to sequential iteration, it is much slower to visit all elements of an array of same size array this way by about 2 orders of magnitude. Note that the scales of these two graphs are different. Not only does this pattern makes vectorization impossible, but it also stalls the pipeline, creating sort of a traffic jam of instructions, all waiting for a single piece of data, the next pointer, to be fetched from the memory. This performance anti-pattern is known as pointer chasing, and it is very frequent in data structures, especially those written in high-level languages that use a lot of allocated, heap-allocated objects and pointers to them that are necessary for dynamic typing to work. This is one of the main reasons why C++ is fast and languages like Java and Python generally aren't. But when talking about latency, it makes more sense to use cycles and nanoseconds rather than throughput units, right? So we can replace this graph with its reciprocal, and what we get roughly corresponds to latency. Not that the cliffs of this graph aren't as distinctive as they were for bandwidth. This is because we are doing random queries, and so there is still some chance of hitting the previous layer of cache, even if the array can't fit into the cache entirely. Um, we can infer latency of each layer using math, or use more direct ways of measuring latency. For example, using non-temporal reads to make sure that we are fetching the elements from specific cache layers. But this benchmark is actually more representative of practical access patterns, because this is what happens when we say query a hash table. We read some random cell, which may or may not be cached, with the chance of it being cached depending on the structure site. So this is more representative. Um, Similar to bandwidth, the latency of all CPU caches proportionally scales with its clock frequency, while the RAM timings similarly do not. We can observe this difference if we change the frequency by, again, turning to boost on, similar to how we did with bandwidth before. So this graph makes a bit more sense if we plot it as a relative speedup. And you would expect that the relative speedup would be twofold for array sizes that fit into the cache entirely, and then roughly equal to for the arrays stored in the RAM, because it's mostly comprised of RAM timings that are independent of the clock. But the latter is not quite true. There is a small fixed latency delay on the lower clock run, even for RAM access. This happens because the CPU has to first check its cache uh, before sending a read request to the main memory to save the RAM bandwidth for other processes that might potentially need it. And this is what we see here when we increase the clock speed. Another very important feature is that the basic units of data transfer in the memory system are not individual bits and bytes, but cache lines. On most CPU architectures, the size of a cache line is 64 bytes, meaning that the memory is divided in block of 64 bytes. And whenever you fetch a single byte, you are also fetching its 63 cache line neighbors, whether you want them or not. So to demonstrate this, we add a step parameter to our incrementing loop, this d here. Now we only touch every dth element while iterating and incrementing the elements of the array. If we run it with d equals 1 and d equals 16, we can observe something interesting. When the array fits into the L1 cache, the strided version completes faster, although not 15 times, but just 2 times as fast. This is because it only needs to do half the work. It only executes a single instruction for every 16th element, while the original loop needed two 8-element vector instructions to process the same block of 16 elements. Both computations are bottlenecked by writing the result back. The CPU can only write one word per cycle, regardless of whether it is comprised of one integer or 8. But as problem size grows, the two graphs meet, despite one doing 16 times less work than the other. This is because, in terms of cache lines, we are fetching the exact same memory in both loops, the exact same cache lines, because 16 integers is exactly the size of a single cache line. And the fact that the strided loop only needs 1/16 of the data that it fetches is irrelevant, because you can't request just one machine board, you need to request the entire cache line. The important practical lesson here is when designing and analyzing memory-bound algorithms, you need to count the number of cache lines accessed and not just the total number of memory reads and writes. It is not entirely accurate, but it's much more accurate than counting memory operations or individual bytes. Also, the fact that the memory is partitioned into 64-byte cache lines makes it difficult to operate on data words that cross a cache line boundary. Because when you need to retrieve some primitive type, say 32-bit integer, you really want to have it located on a single cache line, both because retrieving two cache lines requires more memory bandwidth, and also because stitching the results of that came from two different cache lines in hardware together wastes some transistor space. So this aspect influences algorithm design and how compilers choose the memory layout of data structures. By default, when you allocate an array of some primitive type, you're guaranteed that the addresses of all elements are multiples of their size, which ensures that they only span a single cache line. For example, the address of the first element and every other element of an integer array is guaranteed to be a multiple of 6 bytes, because 6 bytes is the size of int. Sometimes you need to ensure that this minimum alignment is higher. For example, seemed instructions read and write data in blocks of 32 bytes. And it is critical for performance that these 32 bytes read or written belong to the same cache line. In such cases, you can use align as specifier that when defining a static array variable. It guarantees that the beginning of the array will have address divisible by the alignment, 32 in this case, and it can be easily read with simple instructions this way. To allocate a memory aligned array dynamically, you can use standard aligned alloc, which takes the alignment value and the size of the array in bytes and returns a pointer to the allocated memory, just like the new operator does. You can also align memory in sizes larger than the cache line. The only restriction is that the size parameter must be an integral multiple of the alignment. You can also use the align as specifier when defining a structure. Here, whenever an instance of data is allocated, it will be at the beginning of a cache line. So say if it is smaller than 64, when you request any of its fields, you fetch the entire cache line and the entire structure too. The downside is that the effective size of the structure will be rounded up to the nearest multiple of 64. This has to be done so that, for example, when allocating an array of these data objects, not just the first element is properly aligned, but all of them. So some holes will be inserted in the memory layout. This issue becomes more complicated when we need to allocate a group of non-uniform elements, which is the case for structure members. Instead of playing Tetris trying to rearrange the members of struct so that each of them is within a single cache line, which isn't always possible, C and C++ compilers rely on mechanism of memory alignment too. So consider this following toy example. When stored succinctly, this structure needs a total of 1 plus 2 plus 4 plus 1, 8 bytes per instance. But even assuming that the whole structure is guaranteed the alignment of 4, its largest element, its largest member, it is possible that it is allocated on, say, the last 4 bytes of a cache line. And the C variable will be split between the two lines if the structure is stored succinctly. So to fix this, the compiler inserts some unnamed members so that each member gets the right minimum alignment, and also so that the next instance of the structure, when stored sequentially, gets the right minimum alignment too. This potentially wastes space, but saves a lot of CPU cycles. The trade-off is mostly beneficial, so the structure alignment is enabled by default in most compilers. Padding is only inserted before a not yet aligned member, or at the end of the structure to align the structure itself. By changing the order of members in structure, it is possible to reduce the required number of padding bytes and the total size of the structure. So we could reorder the structure members like this. So int goes first, then goes short, then goes char, and then goes the other char. Now each of them is aligned without any padding. If the structure itself is aligned, has an alignment of at least 4. It kind of seems stupid that, and therefore this structure doesn't require any padding, and the size of the structure will be a 4, will be 8 instead of 12. It seems kind of stupid that the size of a structure and consequently its performance depends on the order of definition of its members, but it is required for binary compatibility. So as a rule of thumb, place your type definitions from largest data types to smallest. This greedy algorithm is guaranteed to work unless you have some weird non-power of 2 types, such as 10-byte long double or something like that. Also, if you know what you're doing, you can disable structure padding and pack your data as tight as possible. You have to ask the compiler to do that for you, as such functionality is not a part of C or C++ standard, at least yet. In GCC and Clang, this is done with this packed attribute. This makes the instance of data take just 9 bytes instead of 16 that would be required by alignment with padding, uh, at the cost of possibly fetching 2 cache lines when reading its elements. Next, memory requests can overlap in time. While you wait for a read request to complete, you can send a few others, which will be executed concurrently with it. This is the main reason why sequential iteration is so much faster than point and chasing. The CPU knows which memory allocations it needs to fetch next and sends memory requests far ahead of time. So the number of concurrent memory operations is large but limited, and it is different for different types of memory. So when designing algorithms and especially data structures, you may want to know this number that limits the amount of concurrency your computation can achieve. So to find this limit kind of theoretically for a specific memory type, you can multiply its latency, time to fetch a cache line, by its bandwidth, the number of cache lines fetched per second, which gives you the average number of memory operations in progress. The latency of the L1 and L2 caches is small anyway, so there is no need for a long pipeline of pending requests. But for larger requests, but for larger memory types, there is such a need, and they can sustain 25 to 30 to 40 concurrent read operations. We can also measure the available memory parallelism more directly by modifying our pointer chasing benchmark so that we loop around D, a parameter, separate cycles in parallel instead of just one. So we create D separate cycles, all of them random, and loop around in parallel with this small k array variable. In the experiment, we'll fix the sum of the cycle lengths constant at a few select sizes corresponding to different cache levels and try different D values. We get mostly similar results for all memory types. The performance just scales linearly with the amount of parallel memory lanes, but they all max out between 13 and 17 because if you use more iterators than that number, there will have to be a register spill and performance degradation due to that. You don't always get to the maximum possible level of memory parallelism, register spill being one of the reasons why. but in most applications, a dozen concurrent reads is more than enough. Lesson is make use of memory level parallelism. The CPU can easily have dozens of pending memory operations, and it is a very important consideration that comes up in many data structures, especially those that are easier to implement with pointers, but faster with something else. So, for example, this is why it is much more efficient to implement heaps, stacks, queues, and so on top of global array, also known as vector in C++, as opposed to pointer-based structures like they teach you in colleges. It's also an important issue in hash tables, in search trees, and also in various places where you need um, to store some potentially large objects. You can either store the objects themselves directly as fields, or store objects somewhere else, like on the heap, and store pointers to these objects. Storing the objects themselves makes access to them faster, as you don't need to chase pointers, but makes it problematic to move them if the objects are large, at least larger than the pointer. So there is a natural trade-off here. Um, Another thing that contributes to latency is how you make the memory access. In the benchmark, we didn't use actual pointers, but integer indices relative to a base address, the beginning of the array. If the array is small enough to fit into the L1 cache, this measures around 3 nanoseconds or 4 cycles, CPU cycles per iteration. The memory addressing operator on x86 is fused with the address computation. So the k equals q of k line folds into just a single terse instruction that also does multiplication by 4 and an addition under the hood. Although fully fused, these additional computations add some delay to the memory operations. The latency of an L1 fetch is either 4 or 5 cycles, the latter being the case if we need to perform a complex computation of the address, like we do in this benchmark. And this is a typical situation, not just for these CPUs, but for many others. The complex addressing operation is usually one cycle, takes one cycle more than the raw pointers. So we can make our benchmark run slightly faster if we replace these fake pointers indices with the actual real pointers. This code now runs at flat 2 nanoseconds or 4 cycles for arrays that fit into the L1 cache. Here we save 2 cycles because of a feature of this specific microarchitecture, but on most CPUs we would have saved 1. Unfortunately, there is a problem with using pointers on 62-bit systems. The pointers become twice as large as integer indices. An integer index takes 4 bytes and the pointer takes 8 bytes, making the array spill out of the cache much sooner compared to using a 32-bit index. The latency versus size graph looks like if it was shifted by one power of 2 to the left, well, exactly like it should. But this isn't the case on a 32-bit system, but switching to 32-bit mode has its own disadvantages. So the lesson here is use pointers if the data set is small enough to save a few cycles accessing the data. Otherwise, use indices, maybe wrapped in iterators or something more safe, to save cache space. It may look like a bad software practice, but there is really nothing wrong with them. So also, starting at some level of the hierarchy, the cache becomes shared between different cores. So this lets you add more cores on a single chip, but also poses some noisy neighbors problems, as it limits the effective cache size and bandwidth available to a single execution thread. So on most CPUs, only the last layer of cache, L3, is shared between the cores, and not always in uniform manner. So on Linux, the topology of the memory system can be retrieved with this ls topo command. It generates this graph, And for example, on my machine, I have 8 physical cores. Each core has access to 32 to its own 32 kilobytes of L1 cache, 512 kilobytes of L2 cache, but the L3 cache is shared. Moreover, it is not shared uniformly between all cores. Its total size is 8 megabytes, but it's shared between two groups of 4 cores, each having access to its own 4 megabytes of L3 cache. And there are also more complex topologies where accessing certain regions of memory takes non-constant type, different for each core, which is the case for multi-socket systems that have several separate CPU chips installed. And this has some important implications in parallel computing. The performance of multi-thread memory accesses depends on which cores are running the execution threads. So to demonstrate this, we can run the bandwidth benchmarks in parallel. I like writing code, but more than writing code, I like not writing code. So instead of modifying the source code of that benchmark to run on multiple threads, we can simply run multiple identical processes with the GNU parallel. And to control which cores are executing which processes, we set their processor affinity with a task set. So this combined command runs 4 processes that can run on the first 4 cores of the CPU that share the same L3 cache. So here's what we get when we change the number of processes running simultaneously. The L1 cache, the L1 and L2 caches are private to each core. So the performance is completely unaffected here. But as cores start competing for the shared L3 cache and the RAM, the performance degrades. When looking at the RAM section of this graph, it may seem that with more cores, the per process throughput goes one half, one third, one fourth, and so on, and the total bandwidth remains the same. This isn't quite true. The contention hurts, but a single CPU usually can't saturate all of the RAM bandwidth. If we plot it more carefully, plot the total combined bandwidth of all processes more carefully, we see that the total bandwidth actually increases with the number of cores, although not proportionally with some diminishing returns, but it eventually approaches the theoretical limit of 32 gigabytes per second. The jump in performance between 4 and 5 cores is not a fluke. We specifically set all processes in each experiment to run on the first n cores. And the first and the second halves of this course have separate L3 caches and also memory controllers. If some of the processes were to be scheduled on the other half of the course, there would be less contention for the L3 cache and also in part memory bandwidth. So to show this, let's run another benchmark, but now with bringing the processes to different 4 core groups that don't share the L3 cache. So we will run 2 processes on cores 0 and 1, and 2 processes on cores 0 and 4, which belong to different groups. You can see that when we pin the threads to different core groups, they perform better, as if there were twice as much L3 cache available, which is, in a sense, true. So bandwidth is a shared resource. It is limited, but a single CPU core usually can't saturate it fully. If you have a memory-intensive task, it makes sense to add more cores, but the returns are usually diminishing. This is especially hard to manage in the cloud setting. Say in Kubernetes or similar orchestration systems, there is control in terms of which cores you get or how much memory you can allocate. But the memory bandwidth can be separated between user applications. So increasing the requirements for cores or the memory requirement does not necessarily help. Also, since there is a competition for memory bandwidth, it is also important to remove all interference when benchmarking to get accurate results. This is perhaps the single largest source of noise, except for frequency scaling when benchmarking. Also, unless the system is perfectly symmetrical, and it rarely is, it matters which cores runs which threads. So if the threads use a lot of memory bandwidth or the shared L3 cache, put them apart so that they do not compete for these resources. On the other hand, if the two threads need to communicate, they take logs, for example, they do so via the least common ancestor in the topology. If that ancestor is RAM, the communication could take around 5 times longer than if the ancestor were the L3 cache. So if they need to communicate, it may make sense to do the opposite and put them in the same group. Now, let's get back to the question of memory level parallelism. Well, taking advantage of the free concurrency available in memory hardware, it can be beneficial sometimes to prefetch data that is likely to be accessed next if the location can be predicted. This is easier to do when the processor executes a fixed stream of independent instructions, as it can just pick ahead in the stream of instructions. But sometimes these memory locations aren't in the instruction stream, and yet they can still be predicted with high probability. And in these cases, they can be prefetched by two means, by two ways. First, we can prefetch them explicitly by separately reading any byte in the cache line that we need to uplift in the cache hierarchy. This is called cache prefetching. And second, we can fetch them implicitly by using some simple access patterns such as sequential iteration, which are detectable by the memory hardware that can start prefetching automatically. This is called hardware prefetching. So let's modify the pointer chasing benchmark to show the effects of hardware prefetching. Instead of random permutation, we will now cycle over a permutation that just always points to the next element and loops around at the end. So, and we get the performance as if the array was in the L1 cache, regardless of its size. So the processor here doesn't know for sure that we will be reading the next element, but based on the previous access patterns, the memory controller can speculate that we will need the next cache line and prefetch it ahead of time. Uh, Hardware prefetching can only detect simple enough patterns. You can iterate forward and backward over multiple arrays in parallel, maybe, perhaps with some small strides, but that's about it. For anything more complex, the prefetcher won't figure out what's happening, and we need to help it out ourselves with explicit software prefetching. The simplest ways to do software prefetching is to load any byte in the cache line with the move or any other memory instruction. But CPUs have a separate prefetch instruction that lifts a cache line without doing anything with it. This instruction isn't a part of the C or C++ standard, but it is available in most compilers with the built-in prefetch intrinsic. It's quite hard to come up with a simple example of when it can be useful. So to make the point to chasing benchmark benefit from software prefetch, we need to construct a permutation that at the same time loops around the entire array, can be predicted by hardware prefetcher, and can easily and has easily computable next addresses so that we can prefetch them. And we can get such permutation, for example, if we generate it with linear congruential generator, which is well known and simple random number generator where we multiply the previous number by some constant and add another constant and take modulo some number n. It has the property that if the modulus n is a prime number, then the period of the generator will be exactly that n number. So we get all the properties that we want. It loops around the entire array. It is too hard to be predicted by hardware prefetcher, and we can also compute it easily in advance. If you generate the permutation using this SSG, we get the ability to pick ahead. And if we prefetch one iteration in advance here, the latency becomes almost half of what it was for large enough arrays. Interestingly, we can prefetch more than just one element ahead, making use of this pattern in the LCG function when we expand it, that is repeatedly applied to itself. So to load the dth element ahead, we can do this. And if we execute this request on every iteration, we'll be essentially simultaneously prefetching d elements ahead on average, increasing the throughput not by twofold, but by d times. And this way, we can reduce the average latency arbitrarily close to the cost of computing the next index. So when you know which elements you will need, prefetch them. This is an artificial example, but there are cases where this is useful. They are just too complicated for this talk. Also, it is worth noting that a lot of cases are already handled by the hardware prefetching, and you actually fail more often, in my experience, than not when trying to insert software prefetching into practical programs, especially when you don't know what you're doing. This is largely because you need to issue a separate memory instruction that may compete for resources with the other instructions. At the same time, hardware prefetching is 100% harmless because it has kind of a lower priority than normal requests, and it only activates when memory and cache buses are not busy. Um, Also, prefetching is a mechanism that helps performance, and now I'm going to showcase a really weird but quite frequently occurring feature that hurts it. Consider this the same strided incrementing loop over an array of about 2 million elements that we use to measure bandwidth. But now we will use a step size not 1, not 16, but 226 and 227. So which one do you think will be faster to finish? Well, there are several considerations that come to mind. At first, you think that there shouldn't be much difference, or maybe that the second loop is 227th or so faster because it does fewer iterations in total. But then you recall that 226 is a nice round number, which may have something to do with the SIMD or the memory system or something. Or so maybe the first one is faster. But the right answer is very counterintuitive. The second loop is faster, and by a lot, by a factor of 10. And this is not just a single bad step size. The performance degrades for all indices that are multiples of large powers of 2. There is no vectorization or anything, and the two loops produce the same assembly except for the step size. This effect is only due to the memory system, in particular to a feature called a cache associativity, which is a peculiar effect of how CPU caches are implemented in hardware. So in software, the most common caching strategy is the least recently used policy, where we have some fixed size capacity for cache data, and when we need to add something to the cache, we need to make space for it, and we kick out the element that we have not accessed for the longest time. Hence the name, least recently used cache. In the context of hardware, this scheme is called fully associative cache. We have M cells, each capable of holding a cache line corresponding to any of the n total memory locations. And in case of contention, when we need to add something to the cache and there is no space for it, the cache line not accessed the longest gets kicked out and replaced with a new one. The problem with fully associative cache is that implementing the find the oldest cache line among potentially millions operation is already pretty hard to do in software and just unfeasible in hardware. You can make a fully associative cache that has like 16 entries or so, but managing hundreds of cache lines but managing hundreds of cache lines already becomes either prohibitively expensive or so slow that it's not worth it in the first place. So instead of this, we can resort to another much simpler approach. We can just map each block of 62 bytes, each cache line in RAM, to a single cache line which it can occupy. Say if we have 4,096 blocks in memory, and 64 cache lines for them, then each cache line at any time stores the contents of one of well, divide 496 by 64. You get 64 different blocks. So each cache line can be mapped to 64 different blocks. Direct map cache is easy to implement, as it doesn't require storing any additional meta information associated with the cache line, except its tag, the position of a particular memory block, so that we can tell them apart. The disadvantage is that the entries can be kicked out too quickly. For example, when we are repeatedly jumping between two blocks that are mapped to the same cache line, we will be rereading them on each iteration, leading to lower overall cache utilization. So for that reason, we settle for something in between, direct mapped and fully associative caches. The set associative cache. It splits the address space into equal groups, which separately act as small fully associative caches. It's like sharding in distributed computing. Associativity is the size of these sets, or in other words, how many different cache lines each data block can be mapped to. Higher associativity allows for more efficient utilization of cache space, but also increases its cost. For example, on my CPU, the L3 cache is 16-way associative, while L1 and L2 caches are 4-way associative. So most other CPU caches are also set associative, except for the small ones that house very few entries and can afford full associativity. So there is only one ambiguity remaining, how exactly the cache line mapping is done. If we implemented set associative cache in software, we would compute some hash function of the memory block address and then use its value to cache as the cache line index. In hardware, we can't really do that because it is too slow. For example, for the L1 cache, we need to support a latency of 4 to or 5 cycles, and even taking a model takes about a dozen cycles, let alone something more sophisticated for caching. Instead, the hardware uses the lazy approach. It takes the memory address that needs to be accessed and splits it into 3 parts, from lower bits to higher. The offset, the index of the word within a 62-bit byte cache line. There are 64 bytes, so you need to log 64 6 bits for that. Index, the index of the cache line set, the next 12 bits, as there are 2 to the 12th cache lines in L3, and the tag, the rest of the memory address, just to tell the cache lines apart. In other words, these all memory addresses with the same middle part, this index, these 12 bits, map to the same set. This makes the cache system simpler and cheaper to implement, but also susceptible to certain bad access patterns. Now, so let's get back to where were we. The reason why iteration with strides of 226 causes such 256 causes such a terrible slowdown. When we jump over 256 integers, the pointer always increments by 124. That is 256 by 4. This means that the last 10 bits of the address remain the same. The cache system uses the lower 6 bits for the offset and the next 12 for the cache line index. And since the last 10 bits remain the same, we are effectively using only 8 bits of the available 12 for the L3 cache, which has essentially the effect of shrinking the usable cache space by 16. And so, because we are using 8 bits for index instead of 12. And so it splits the array spills in the RAM because there is less L3 cache. That is an order of magnitude slower, hence the slowdown. Performance issues caused by cache sensitivity effects arise with just remarkable frequency in algorithms because for multiple reasons, programmers just love using powers of 2 when indexing arrays. Because it is easier to calculate the address of a multidimensional array um, um, if the last dimension is the power of 2, as it only requires like a binary shift instead of a multiplication. It is easier to calculate modulo a power of 2, as it can be done with a single bitwise AND. It is convenient to and often necessary to use power of 2 problem sizes in different divide and conquer algorithms. It's also the smaller integer exponent, so it is attractive to use for benchmarking sizes. Also, more natural powers of 10 are by transitivity. Since 10 is divisible by 2, then powers of 10 are divisible by 2, and large powers of 2. Yeah, so there is a natural tendency to use powers of 2, so it is often arises in different algorithms. So, for example, matrix multiplication, just standard naive multiplication, is about 30% slower for matrices of size 226 than for matrices of size 227, for exactly the same reason, because in the inner loop of the matrix multiplication, we are iterating in the steps of size of the matrix size, and therefore we are jumping in increments of 226, which would again map to the same set and reduce our effective cache size. Also, binary search is 20% slower for arrays of size 2 to the 12th than for arrays of size 2 to the 12th plus 123. This is slightly more complicated. When the array size is a multiple of a large power of 2, then the indices of the quarters elements, the ones we likely request on the first dozen or so iterations, will also be divisible by some large power of 2 and map to the same cache lines, kicking each other out and causing a 20% performance decrease. Luckily, such issues are more of an anomaly rather than serious problem, and the solution is usually simple. Avoid iterating in powers of 2, make the last dimensions of multi-dimensional arrays slightly different size, or use any other method of inserting holes in the memory layout. Or better yet, make it so that you don't have jumps in the first place, because when you are doing jumps, you are probably doing something wrong anyway. So, for example, the optimal algorithms for matrix multiplication and binary search both permute the input elements so that the reads are as sequential as possible during the algorithm execution. Um, I initially wanted to name this talk "What You Need to Know About Memory" or something along these lines, but I realized that this talk is very far from being enough. There are many related cool things that I intentionally did not cover, and I would like to at least mention them so that you can read up on them later. So first, there are tools for memory analysis. For more complicated programs, you may want to use these tools that let you measure how much cache misses or page faults your program produces. Perf and similar statistical profilers can do that, and cache-grind can also tell you where these cache misses are happening. Also, to execute any sequence of instructions in a program, the processor needs to first load it and to first load these instructions, which are stored just in memory, just like data does. And to speed things up, there is a separate system of instruction caches and different program layout optimizations, for example, that try to group hot code together with hot code so that they occupy the same cache lines and memory pages. RAM is also quite different from the CPU caches, and it has its own timings and quirks. Also, performance becomes much harder to assess on NUMA systems when you have multiple CPU sockets or multiple RAM sticks, especially different RAM sticks. There are also complicated things happening when multiple cores want the same cache line or do other communication. External memory can also have some very specific properties that are especially important for implementing high performance storage system. How operating system interacts with storage devices and all that, how it ensures that the stored data is correct and is not corrupted by like colliding cosmic neutrinos and stuff. And the last and definitely not least, how memory allocation and garbage collection happens, or how it should happen. These all are large, very important topics with separate books written about them. So no, you do not know everything you need to know about memory. Nobody does. So I highly encourage you to read up on them. And in terms of more immediate reading recommendation, first, well, there is my book that covers everything in this talk and a lot more. There is also a famous manual titled What Every Programmer Should Know About Memory by Ulrich Draper. It is 114 pages of two-column text, so very comprehensive. It was written back in 2007, but it is still very relevant, still great, and highly recommended. And there is also Timur Dumler, who is also a speaker at this conference, by the way, who did a talk titled One Fast C++, Know Your Hardware. That is very similar in style to this one, but covers other things too. So if you watched to this point, you probably like this talk. And if you like this talk, you will definitely like Timur's talk. So that's about it. And thank you, everyone.
So, Sergey, thank you so much for that amazing talk. I think we will take questions in the lounge outside of here. So